Hey guys, and welcome back to another video. In this video, we'll be talking about exponential and logarithmic equations and inequalities. Alright, so let's get right into it. Alright, so first off, let's discuss some important properties that we'll be using to solve these equations. So the first one is, suppose you have log base b of b to the x, right? This is just going to give you x back, okay? So as an example, like if you had log base 2 of 2 to the x, right? The log base 2 and 2 will cancel, and you just get x back, okay? And then the other one is like if you have like b to the log base b of x power, then b and log base b cancel, and you just get x back. So for example, if you have e to the ln x, then e and then ln cancel, because remember ln is just log base e, so those cancel, and you just get x back, okay? And these two are super useful in solving the exponential and logarithmic equations, because for exponential, for example, if you have like something like b to the x, you just take log base of that b of both sides, and then it just cancels. You just get x in the bottom. So that's super nice. And then if you had like a logarithmic thing, you just take b to both power, like b to that power, b to that power, and then the b and the log of the base b will cancel, so you just get x, and then is equal to some expression. Okay, and then the final, arguably the most useful one is the change of base formula. So what this one says is if you have like log base b of x, right? This is equal to log base a of x over log base a of b. So basically, if you have some log base b of x, then you could just take log base of some base of the inside of x over log base, the same base of the b. So for example, let's say we had like log base 5 of 16. This, according to the change of base formula, would equal, and let's use like log base 10 for example. So it'd be log base 10 of 16 over log base 10 of 5. All right. And the reason this one is so useful is because when we're solving the exponential equations, right, there's two ways that you can go about it, right? The first way is like if you had like 2 to the x, for example, you could just take log base 2 of both sides, so then the 2 and the log base 2 cancel, and you just get x, right? That's one way to solve it. The other way to solve it, you just take log of a common base of both sides. So for example, you could take log base 10 of both sides, or like log base e, right, ln of both sides, and then that way you can just do it that way. And then if you do the first way, you will get like some expression in terms of like log base 2. Like for example, you get something like this, log base 5 of 16. And if you do the other way, you get like this. And then at first glance, it may seem like they're different answers, but then if you know the change of base formula, you can quickly realize that they're actually the same answer, just written in different forms. And then the second reason this is so useful is if you want like for example, if you got that x is equal to log base 5 of 16, right? And you want to approximate it, that you want to put into a calculator, then on your calculator, there's no button for log base 5, right? But if you convert it to log base, if you convert it using change of base formulas to like log base 10 or like ln, those buttons are on your calculator, and then that makes it easier to put this whole expression into your calculator. Okay, so those are the two main reasons why this change of base formula is so powerful. All right, so now having that covered, let's do some examples. So first one, starting off relatively easy. Let's say we have 3 to the x is equal to 81. So for this one, you could just like take log base 3 of both sides, and then you get like log base 3 of 3 to the x is equal to log base 3 of 81. And then remember, log base 3 of 3 cancels, so you get x is equal to log base 3 of 81 is just 4. So you just get x is equal to 4. Okay, so this is valid. But what I recommend is that before you even solve doing that, you can just like notice if the other, like the right hand side in this case, if it's a power of 3. Because if you knew that, like if you knew that 81 is just 3 to the power of 4. Okay, so then now you have 3 to the x is equal to 3 to the power of 4. That must mean that x is equal to 4. Because exponential functions and logarithmic functions are 1 to 1. Meaning that for each input, there's exactly one output. Okay, so that's like a much easier and faster way to get to the answer. All right, so let's do another one. So if you had 5 to the 7 minus x is equal to 125. So again, you could just take log base 5 of both sides and then get the correct answer. But then if you just like look at this for a little bit longer, you can notice that 125 is just 5 cubed. And now you're just solving 7 minus x is equal to 3, which is much easier. and you get x is equal to 4 again. All right. Okay. So now let's do a little bit, some more complicated ones. So suppose we had 5 to the 3x is equal to 16. So now you do have to do it like the other way, right? Because 16 can be written as 5 to any power. But again, there's two ways to do this. So the first way is like I've been saying, you could just take log base 5 of both sides. So you have log base 5 of 5 to the 3x is equal to log base 5 of 16. And then log base 5 and 5 cancel. So you just get 3x is equal to log base 5 of 16. And then x is equal to this quantity divided by 3. Okay? So this is a valid answer, right? This is the correct answer. And then the other way to do it is, like I said, you could just take log, like the common log of both sides, or like natural log of both sides. So if you take common log of both sides, then you get the following. And then from properties of logarithms, you know you could take the exponent out front. So you get 3x log 5 equals log 16. And then divide both sides by 3 log 5. Because then this cancels and you're just left with x is equal to log 16 over 3 log 5. And this is what I was referring to earlier when I said you get two different answers, or two answers that look different but are actually just the same. Because now if we look at log base 5 of 16, we can convert this to common log using change of base. So we get, this is just equal to log of 16 over log of 5. And then if you substitute that back into here, indeed you get this answer. So they're actually just the same, just written in a different form. Okay? But yeah, both of these are the correct answer, and then there's two different ways to solve this one. Okay? All right, good. All right, let's do another one. So we had like 4 to the 3x plus 2 equals 71. So again, 71 cannot be written as 4 to any power, so you have to do it the traditional way, like the common, the way that always works. So the first one, you just take log base 4 of 4 to the 3x plus 2 equals log base 4 of 71. Log base 4 and 4 cancel, so you have 3x plus 2 is equal to log base 4 of 71. And then solving for x, you get log base 4 of 71 minus 2 all over 3. This is one. So this is the answer, one of the valid forms. And then again, the other way, you just take like common log of both sides. Okay, and then you take the exponent out front, so you get 3x plus 2 log 4 is equal to log 71. And then this is a very important thing actually, is that when you take this out front, you have to put parentheses around it. Because what a lot of kids will do is they'll like forget the parentheses, right? And then now it looks like only the 2 has the log 4 attached, even though the whole thing does. So it's very important that you put parentheses around it when you take the exponent out front. And then now you can just distribute, so you get 3 log 4x. Put the x right here actually. 3x log of 4 plus 2 log 4 is equal to log 71. And then solving for x, you get 3x log 4 is equal to log of 71 minus 2 log 4. And then x is equal to log 71 minus 2 log 4 all over 3 log 4. And then if you just convert this answer to like log base 10 using change of base, you should get the same answer as this, right? Because these two should be equivalent. All right. So now let's talk about like natural base, right? So if we had like e, so let's say we had like e to the 2x minus 4e to the x plus 3 equals 0. Okay, so how would you solve this? Well, if you notice, this is just a quadratic, right? Because here you just have e to the x times e to the x, right? Because if we have e to the x times e to the x, then this is just equal to e to the x plus x, because you just add the exponents, and so you get e to the 2x. Okay, and so then if you have e to the x times e to the x, that's just equal to e to the x squared. So that's how I'm going to write this. I'm going to write this as e to the x squared, and then minus 4 e to the x, and then plus 3 equals 0. So now, if you just like in your mind replace e to the x with like some other variable like u, let's say, then you get like u squared, I'll let you write it out, u squared minus 4u plus 3, right? So if we had like u is equal to e to the x, then this whole thing just transforms into this. And this is a quadratic, so we can just factor this. And if you factor it, you get u minus 3 times u minus 1. Okay, and then from this first one, you get that u is equal to 3. And from the second one, you get u is equal to 1. But remember, we're not looking for what u is. We're trying to solve for x. So you have to back substitute. So then u is equal to e to the x. So e to the x is equal to 3, or e to the x is equal to 1. And then from here, you could just take natural log of both sides. Because if you take natural log of this side and then natural log of this side, natural log of e cancels, so you get x is equal to natural log of 3. And then same thing here, natural log of e cancels, you get x, that's equal to natural log of 1. Okay? And then from here, notice that natural log of 1 is just 0. And then you just have natural log of 3. So these are the two answers. All right? Okay, good. So now let's move on to logarithmic equations. So we have log base 4 of 2x minus 3 equals log base 4 of x times x minus 2. And I will say that for logarithmic equations, it's super duper important that you check your final answer, because the domain for logarithmic functions is that is from 0 not included to infinity, right? So if you get like an answer and then you plug it back in here and then you get like something inside the log that's less than 0, less than or equal to 0, then it's extraneous, right? So for like exponentials, you also should check your answers, but like for that one, it's not that important because the domain is negative infinity to infinity. So at that point, you're just checking like to see if you got like the correct solution, right? You're not checking to see if it's extraneous or anything. But for this one, it's super important to check because it might be an extraneous solution. Okay, so with that in mind, let's solve this. So, okay, so first of all, notice that we have log base 4 of this thing is equal to log base 4 of this thing. And logarithmic functions, just like exponential functions, are one-to-one, meaning that for every input, there's exactly one unique output. So that means that we can just equate the insides. So we just get 2x minus 3 is equal to x times x minus 2. Okay? And so simplifying this, you get 2x minus 3 is equal to x squared minus 2x. And you get x squared minus 4x plus 3 equals 0. And then factoring this, here's the quadratic. So x minus 3 times x minus 1 equals 0. So either x is equal to 3 or x is equal to 1. So now this is where it's super important to like plug it back in here and check your answers. So if you put 3 into here, you just do it in your head. 2 times 3 is 6, minus 3 is 3. So that's greater than 0. Good. So it works in this one. And then putting into here, we have 3 times 3 minus 2, which is 1. So 3 times 1 is 3, also good. Log base 4 of 3 equals log base 4 of 3, good. So this one works. So x equals 3 is a solution. Okay? But now if you put 1 into here, just looking at this one, you have 1 minus 2, that's negative 1. So in here, you have a negative value. So x minus 1 does not work, right, as extraneous, because you get a value that's outside of the domain. That means that the only solution for this equation is x equals 3. Okay, good. And like graphically, that should make sense, right? Because remember, it's 1-to-1. So there should only be one x value that satisfies this equation. So just the fact that you got two x values means that one of them has to be extraneous, right? All right, let's do another one. So let's say we had ln of 3 minus x squared equals 7. So for this one, this is when you'd have to like do e to this power equals e to that power. Okay, because then now e ln cancel, and you just get 3 minus x squared is equal to e to the power of 7. And then solving for x squared, you can do x squared equals 3 minus e to the power of 7, and then take plus minus squared on both sides. So x is equal to plus minus root 3 minus e to the power of 7. 3 minus e to the 7th. Notice that e to the 7th has to be bigger than 3 because e is greater than 2, right? E is like approximately 2.71. So then that raised to the power of 7 has to be greater than 3. So that means that this inside part is negative. And so you have a square root of a negative number, no solution. Okay, so that's actually another very important thing to check for, is like if you have a square root, you have to make sure this thing is positive, which we just found it's not, right? Because e to the 7 is bigger than 3, so 3 minus something bigger than 3 is going to be negative, and the square root of a negative number is imaginary, and we're dealing with only real solutions in this section. Okay, so yeah. All right, so now let's move on to inequalities. So let's say we had log of x minus 8 plus log 2 less than or equal to log of 3x plus 4. Okay. So the first thing you're going to want to do for these problems is you want to get one log on each side, right? So you have log of something on this side, and you want to get one log on this side. So using logarithmic properties, like we learned in the last video, we can combine these two as just log of 2 times x minus 8 is less than or equal to log of 3x plus 4. And then from here on out, it's just the same thing as solving equations, right? So you have log of something is less than or equal to log of another thing, meaning the insides have to be less than or equal to each other. So you could just like kind of get rid of the logs, and you get 2x minus 16, just distribute the 2, is less than or equal to 3x plus 4. And then isolating for x, you get that x is bigger than or equal to negative 20. Okay, and then again, this is another part where you have to be super careful because you have to check for the domains of each of these. The domain of log of x minus 8 is that x has to be greater than 8. The domain of this one is x has to be greater than negative 4 over 3. Okay? And our solution is that x is greater than or equal to negative 20. So you want to take this union the most restrictive domain. So what I mean by that is like, if we just look at the domains, right? Here we require x to be greater than 8. Here we require x to be greater than negative 4/3. So which one is more restrictive? This one, right? Because this one includes lesser values in the domain. So we're going to take this domain, the more restrictive one, and union it or intersect it with this one. So this is just the same thing as saying negative 20 included to infinity, and then intersected with 8 to infinity. So now which one is the most restrictive one? It's still this one, right? So the actual answer is just 8 to infinity. So whenever you're solving these inequalities, it's the same thing as solving equations, but then you also have to check the domains of each of the original logs and then see which one is more restrictive, the solution or like the domain. And if the domain is more restrictive, then you just take the domain. If this one's more restrictive, then you just take that, right? All right, let's do another one of these. So let's say we had log base 2 of 2x plus 6 is greater than 3. So the first thing I'm going to do is I'm going to write the domain for this one. The domain for that one is x has to be greater than negative 3. Okay, so if you get anything that, like, for example, if you got like x is greater than negative 10, we're going to take this one because this one is more restrictive. Okay. Anyway, so now we solve this. So we have log base 2 of something is greater than or equal to 3. So I'm just going to do 2 to that power and then 2 to that power. So then the 2 and the log base 2 cancel. So you just get 2x plus 6 is greater than 2 cubed. And then we can just rewrite 2 cubed as 8. Okay. And then solving for x, we get x is greater than 1. So now you have to look at x is greater than negative 3 and x is greater than 1. Which one is more restrictive? This one. So this is just your final answer. So writing an interval notation, 1 not included to infinity. All right. Last one. We have 3 to the x plus 2 minus 4 is bigger than 23. So let's move the 4 over first. So we have 3 to the x plus 2 is bigger than 27. And then for this one, we can notice that we can write 27 as a power of 3. So that's super nice because we have 3 to the x plus 2 is greater than 3 cubed. And then just like before, this means that x plus 2 must be greater than 3, meaning that x must be greater than 1. And for these ones, we have exponentials. Now you don't have to check it, right? You only have to check it mainly for like logarithmic equations because the logarithmics have that restriction on the domain x is greater than 0. But for exponentials, the domain is all real numbers, so you don't have to check anything. And this is just the final answer, starting an interval notation, 1 not included to infinity. All right. But yeah, that's pretty much it for exponential and logarithmic equations and inequalities. If you found this video helpful, please make sure to subscribe and definitely leave a like. I'll see you guys in the next video.